Welcome to our lecture online, and here in this video and the next several videos after this one, we're going to take a closer look at Ampere's law. Ampere had a really clever idea. He assumed that, again, correctly of course, because we already realized that when we took measurements, that if we had a current running through a wire, we knew that there was a B field around the wire. Whenever there's a current, there's going to be a magnetic field. And the direction of the field can be found by taking your thumb, pointing it in the direction of the current, and your fingers would curl in the direction of the magnetic field. And we also knew that the farther out you went, the weaker the magnetic field became. The closer you got, the stronger the magnetic field became. So let's take a look at this again, but now we're going to look at it from the top down. So now we have the current coming out of the board like this. Again, using your thumb, you point your thumb in the direction of the current, and your fingers will curl in the direction of the magnetic field. Ampere realized that if we took an arbitrary point away from the current, let's say that this is a distance r away from the current, that he realized that if we integrated all the way around this circle right here, and the integral that he was thinking about is we're thinking a continuous integral all the way around the circle of the strength of the B field and the direction of the B field dotted, we have the dot product here with the dl. And let me show you in just a moment what this is. So this is what we call a continuous integral going all the way around the circle, continuous loop integral. We multiply the strength of the magnetic field, the magnitude of the magnetic field, and the direction of the magnetic field we multiply that with the direction that we're moving around the path like that. So a dl would be a very small little line segment. So right there, so we take a very small little line segment, infinitesimally small, and of course if we're going to integrate around the circle in a counterclockwise direction, that small little element there, that length element there, is going to be very, very tiny, pointing in that direction. And notice that the direction of the magnetic field and the direction of that line segment is exactly the same. Also remember that the dot product, and let me write it over here, that the dot product between the magnetic field and the small little line segment is equal to B times dl times the cosine of the angle between the two. Now notice that the angle here between the two should be 0 degrees because the B field is pointing in that direction right there, and the line segment is pointing in that direction, so they're parallel at the time. That means the angle between them is 0, and of course the cosine of the angle between them, the cosine of 0, that would be equal to 1. So this becomes 1, so simply B times dl. Now the reason why this works is because we took everything in perfect symmetry. We wanted to make sure that the path that we take for the integral is a circular path and that the radius remains equal all the way around. If we didn't do that, if we put this on the side here, and so the radius changed in direction, then the line segment dl in the direction of the magnetic field wouldn't always be the same. The angle between would constantly change, and of course that would vastly complicate that integral, and we'll see that in our next video why that is so. So anyway, we now know that B dot dl is simply B times dl because the angle between them is 0 and the cosine of 0 is 1. And Ampere realized that this line integral, no matter how you do the integral, no matter what the path length is, no matter what the direction of the path is, or the strength of the magnetic field, if you do a complete integral like this, he said this will always be equal to mu sub naught, which is the permeability of free space, times the current that's inside this line integral. So times I enclosed inside the integral. And of course, in this case, I is right here. It's the current coming out of the board. And so he realized that that would be the case. Now notice that if we were to take R to be larger, then the line integral a bit longer. So you have a long integral, but then also the magnetic field strength would be weaker further out. And it turns out that integral, regardless of where you do that integral, you can do the integral right over here on the small circle. You could do the integral over here for a big circle. And again, it doesn't matter where, because he realized that the line integral of the strength of the field at that distance multiplied times the length around that path would always be the same number, would be a constant number, and it would always be equal to mu sub naught times the total current enclosed in that integral. So in this case, if we're going to integrate all the way around, and we know that the radius is r, all the way around, of course, is going to be 2 pi r, and so therefore the strength of the field B times the total length of the integral, 2 pi r. And the reason why we can do that is because the strength of the B field does not change anywhere along the loop. As long as we stay on the same distance r away from the current, the strength of the B field will always be the same, and no matter where we go in the path, the direction of the magnetic field and the direction of the line segment is always going to be parallel, and therefore we can write this. So we know that this is equal to mu sub naught times I enclosed, and therefore we can say that the B field, the magnetic field, is equal to mu sub naught times the current divided by 2 pi times r. And notice that is the exact same equation that we get when we simply take a line right here with current and we start integrating it across the whole overall length, and we take the position right there at the edge of that circle. We get the very same equation no matter how we try to get the B field, the magnetic field at that point. But you can see that Ampere's law in this case is a really easy method to use, very handy in all kinds of situations. As long as we pick a path where the magnetic field is the same along the path, then that makes it a really easy integral. We can always easily find the strength or the magnitude of magnetic field that way. So that's how we do that.